Mars has always seemed like humanity's obvious next destination. But what if the real key to the future of space isn't Mars at all? What if it's Ceres, a small frozen world in the asteroid belt, that could one day become the fuel station and supply hub for the entire solar system? In this video, we're asking a bigger question than which world looks more exciting. We're asking which one actually makes more sense. Mars is the easy hero of public imagination. It's been part of human dreams for decades, probably centuries if you want to go all the way back through literature and ancient astronomy. It's got land, it's got weather, it's got sunlight and a day length that's shockingly close to Earth, just slightly over 24 hours. It's a planet we can all picture humans walking on in spacesuits, growing food under domes, driving rovers across red plains, and maybe, just maybe, one day turning deserts into green valleys. It feels like a place where people could live, not easily, but in a way that makes it a world worth calling home. Ceres, on the other hand, doesn't really inspire the same kind of imagery. It's not the sort of place that gets written into adventurous sci-fi or romanticised in folk tales about pioneering a new world. And at first glance, it probably doesn't even feel like it's in the same conversation. A dwarf planet smaller than some countries on Earth, far off in the middle of the asteroid belt. It's just this icy little world outshined by the spectacle of Mars. But what if that's exactly why it matters? Ceres forces us to stop and ask, where are we going? Not just physically, but in how we think about space. Are we looking for another home? Or are we building a practical staging ground in the grand logistics game of expanding beyond Earth's orbit? Because here's the thing, Mars is a dream rooted in settlement. We dream of cities with rudimentary but hopeful infrastructures, of dust-laden greenhouses where the first potatoes are grown for hungry colonists, of a new chapter in human history where we could one day say, here is Mars, the second world of humans. Mars asks us to think about how life might evolve under new and brutal conditions, but on a world big enough, stable enough, and Earth-like enough to make it plausible. Ceres, by comparison, is not about the settlement dream, it's about the infrastructure dream. It's not out there whispering, come and live with me. It sits quietly, more utilitarian. It's effectively editing the space conversation to say, you want to explore the deep solar system, you want to go to Jupiter, build industry out here, build logistics out here. A place rich in water and positioned well to support future operations doesn't need a skyline of futuristic domes to earn its place in the solar system. Ceres is smaller than the largest nations on Earth. Texas has a land area larger than its surface, but it's still the biggest object in the asteroid belt. That gives Ceres unique significance. It's not massive by planetary standards, but it's no ordinary asteroid either. It's 940 km, approximately 583-mile wide body, sits in a fascinating middle zone, geologically interesting and compositionally rich without being overwhelmingly planet-like. It doesn't give us sweeping deserts or Olympus Mons-style volcanism, but it does give us one undeniable advantage: water. Lots of water-bearing material beneath its surface, frozen in abundance. Frozen water changes everything in space exploration. We're not just talking about something human settlers would drink with breakfast. Water is truly the Swiss Army knife of space materials. Split into hydrogen and oxygen, it becomes rocket fuel. Used in radiation shielding, it protects crews from deadly galactic particles. Combined with nutrients and sunlight, it becomes the lifeblood of a closed agricultural system. A place with accessible water isn't just somewhere to go. It's a logistical jackpot, the kind of node that could help sustain everything from human missions to robotic exploration fleets. Now, there's an undeniable reason why Mars still captures the majority of attention and resources when it comes to serious long-term roadmaps. The metrics of human gravity tell part of that story. Mars's gravitational pull is 3.71 meters per second squared, about 0.38 g compared to Earth's 1 g. That's weak, certainly, but at least it's a level of gravity that biology understands. People who weigh around 82 kilograms, or about 180 pounds on Earth, would weigh closer to 31 kilograms, or 68 pounds. Lifting something does become easier there. But importantly, you'd still perceptibly weigh something. Your muscles would still resist. Your bones would adapt somewhat to that load. Over months or years, this partial gravity might not entirely prevent physical decline, but it could dramatically slow the atrophy seen in microgravity environments during space flights. Ceres? Here's the staggering truth. It has almost no gravity to speak of. At merely 0.27 meters per second squared, or 0.028 g, quite literally 1/36th of Earth's pull, a human body would essentially feel like it weighs closer to 5 pounds, 2.3 kilograms, no matter how big, strong, or earthborn they started out. Imagine walking through a world where every tiny motion threatens to launch you into awkward, slow-motion flight. What does that do to your body in the long haul, your muscles, your joints, your digestive systems, your ability to nurture life? The honest answer is we don't entirely know, but we do know this. Living long-term in ultra-low gravity, without some engineered solution like rotating habitats to simulate gravity, might challenge human biology at a level somewhere between deeply taxing and completely unsustainable. So there it is, the basic tension of the whole discussion. Mars is harder to imagine as an accessible refueling depot or resource processing hub for solar system operations, but for a settlement, it starts feeling real, if brutally ambitious. Ceres in turn starts competing when you think about the future in terms of transportation and supply chains. It's easier to take off from and export stored resources out to other missions. It's a gateway to the asteroid belt. But living there permanently, building something that feels like its own world, that quickly becomes harder to picture. Keep that tension in mind because it's going to steer us through every piece of this debate. Whether you think we should go to Mars first, or Ceres first, or both, or neither, depends almost entirely on how you define success for humanity in space. Is it survival, expansion, science, industry, or the founding of new civilizations? As we go deeper into the details, you'll see that Mars speaks to one vision, Ceres speaks to another, and where humanity goes next will ultimately say more about what we value, what we're willing to sacrifice, and what kind of future we see for ourselves, than it does about dust, water, or rock. Ceres is not a small Mars, and it's crucial to kill that misconception early. It might be easy to think of it as just a downsized version of the Red Planet, because both are discussed as targets in the same space exploration conversation. But that's fundamentally incorrect. Mars and Ceres are not just two different sizes of the same idea, they are two completely different types of worlds that belong to entirely different categories of celestial bodies. Understanding this difference is absolutely essential to appreciating why the debate between them is so nuanced. Mars is undeniably a terrestrial planet. It has a dense history etched into its surface, volcanoes that once erupted with lava, canyons carved out by ancient tectonics and erosion, and what appears to be evidence of long-gone riverbeds that hint at liquid water from billions of years ago. It has polar caps made of water ice and carbon dioxide ice that shift with the seasons. There's weather on Mars, an incredibly thin atmosphere of mostly carbon dioxide, and even storms, dust storms that can blanket the entire planet. It feels alive in its geology, even if not in biology. Mars is a world shaped by planetary-scale processes, much smaller than Earth, but recognizable as a planet. You could look at its surface and almost intuitively understand it as an alien twin of our world. Ceres is none of that. Ceres isn't just smaller than Mars, it's smaller than some moons. Its widest diameter spans 940 kilometers, or about 583 miles, which is less than the distance from New York to Chicago. That essentially puts it on the upper range of what we call a dwarf planet, a body that's massive enough to round itself into a sphere but not massive enough to dominate its orbit. Ceres has no atmosphere to speak of, no violent global reshaping from volcanic or tectonic activity, no sprawling deserts or scarred channels left behind by ancient rivers. What it does have, though, is water, or more precisely, water ice. Lots of it. Beneath its surface, Ceres seems to hold an enormous reservoir of water-bearing material mixed with rock, salts, and other components. It's this combination, ice-rich yet fundamentally different from a terrestrial world, that defines the conversation about Ceres and sets it apart as something unique. Comparing Mars to Ceres is less like comparing Earth to Venus, and more like comparing Earth to an exceptionally hydrated asteroid with some unusual planetary features. And here's another thing. People often get swept up in size comparisons, but in this case, where a world is located actually matters far more than how large it is. Mars is situated neatly at roughly 1.5 astronomical units from the Sun, 1 AU being the distance from Earth to the Sun. That puts it in a pretty convenient spot in the solar neighbourhood. When you look at the Sun from Mars, it's smaller than the Sun as seen from Earth, but it still offers enough light for solar panels and passive heating systems, barring disruptions like those infamous dust storms. Ceres sits much, much farther out at 2.77 astronomical units on average. That's almost twice as far from the Sun as Mars, and the difference is dramatic. Remember, sunlight diminishes as the scale of the distance. By the time the Sun's light reaches Ceres, it's less than 15% as strong as it is at Mars, and given that weaker sunlight relying on solar panels is a much harder proposition. Mars is dim, Ceres is deep sea. Deep space dim. That affects everything. It's not just a technical question of solar energy availability, it redefines how you think about power architecture entirely. Instead of relying primarily on solar power, a Ceres base might require nuclear energy as its backbone almost by default, but that introduces its own logistical challenges. Moving on to surface conditions, the contrast gets even sharper. Mars is a planet with reasonably familiar terrain. You can land a spacecraft on its open plains, drive rovers across its deserts, and drill into its ancient soil. Mobility is straightforward, constrained mainly by dust and terrain roughness rather than exotic physics. You can haul heavy machinery, dig for resources, and even imagine one day building large organised colonies with roads and vehicles. Think deserts and canyons on an alien scale, but still tangible. Ceres? Ceres is nothing like that. The gravity is so low that movement itself changes. Walking wouldn't feel normal. A single hard push against the surface could send you into a slow, awkward floating arc. Machinery designed for weight and traction wouldn't work intuitively. You'd need things like anchors and tethers just to keep equipment from drifting. Excavation could look bizarre, digging into material that's not just brittle, but weirdly delicate when touched in ultra-low gravity. Even construction would mean dealing with entirely foreign challenges. Something as simple as driving a spike into the ground could cause unintended recoil. Ceres operates more like a platform for low-gravity operations than anything resembling a normal landscape. Then there's the day-night cycle. You might assume that a faster rotating world would be more chaotic, but for machines, the opposite is true. Ceres completes a full rotation roughly every 9 hours, giving it short days and nights compared to Mars' 24.6-hour day, already close enough to Earth's to feel natural for human time management. On Mars, humans can adapt comfortably to the rhythm of a day just slightly longer than Earth's. That kind of subtle continuity with Earth is huge. It reduces the mental and physiological strain across years of habitation. By contrast, Ceres' 9-hour day might not matter much to automated systems, but for human crews relying on circadian rhythms for overall health, it would be a challenge. You'd essentially have to create a totally artificial timekeeping system in habitats to avoid throwing people's bodies into perpetual jet lag. So why, you might wonder, does Ceres even attract any interest from serious space planners if it's so foreign, so different, and arguably so inconvenient for humans in key ways? The answer is because of what it could represent. If humanity ever becomes serious about large-scale space industry across the solar system, the asteroid belt becomes critically important, and into the asteroid belt Ceres is king. It's big enough to serve as a useful operational anchor. It's rich enough in water to matter for resource extraction. And its laughably low gravity means it's far easier to move mined materials like water, fuel or minerals off its surface than it ever would be from Mars or Earth. You can send material into orbit or further destinations with barely any energy compared to the effort required to launch out of larger gravity wells. Ceres, in plain terms, isn't a place to live comfortably. It's a place to process materials, refuel, and dispatch missions deeper into the solar system. Mars is an invitation to a planetary struggle. Ceres is a foothold in the logistics chain. If Mars asks us to think of second cities, Ceres asks us to think of fueling stations, warehouses, and depots. That contrast defines everything. No part of this comparison works if you expect Ceres to compete with a dream of sunsets over Martian valleys. It wins its value in a completely different league. And now that we understand the kind of world Ceres actually is, the rest of this conversation can finally take shape around its unique purpose versus Mars' ambitions. Getting to Mars is already hard. Even under favourable conditions with current or near-current technologies, reaching the red planet requires a travel time of roughly 6 to 9 months. That number isn't arbitrary. It reflects the combination of the rocket's propulsion capability, the alignment of Earth and Mars, and the trajectory used. It's a demanding mission, but also one that's at the edge of human endurance and logistical planning. Now take that sense of difficulty and stretch it. Because if Mars feels like a distant challenge, then Ceres should feel light years away. Not just in literal distance, but in terms of everything that distance multiplies. A crewed mission to Ceres using today's propulsion technologies wouldn't just be a more difficult Mars trip. It could easily take several years. Thinking about that, not months, a stretch that's already psychologically and physically punishing, but possibly 2, 3, or more years just to get there. And that transit time isn't just an inconvenience. With every passing week or month, the demands on a mission compound themselves. More food is required to keep a human crew functioning. More radiation protection is needed to shield them from the galactic cosmic rays and solar particle events that hammer deep space vehicles. Spacecraft already face extreme weight limits on supplies, and extending travel times exponentially raises the strain on how much stock you can launch, while staying within acceptable margins. Don't forget spare parts, machines break down, and being years away from Earth means you have to bring backups for everything, or the ability to build repairs on site. Psychological strain also becomes unavoidable. People are remarkably resilient, yes, but putting a crew in confined quarters, isolating them from Earth, and asking them to wait and wait for 2 or 3 years is a human experiment in endurance unlike anything in history. It's not an exaggeration to say that with every extra month, the risk of failure in health, systems, or morale rises. But here's the thing most people don't think about. Space travel isn't just measured linearly in distance. It's not like taking a road trip and treating Ceres as twice as far as Mars, because it's nearly twice the astronomical distance from the Sun. What truly defines missions in space isn't distance, it's energy. Specifically, the change in energy required to leave one orbit and insert yourself into another. This is what scientists call delta V, or the change in velocity. To put it more simply, how much your spacecraft needs to accelerate, decelerate, and maneuver during its journey. A mission to Mars, for example, requires much more delta V than a mission to the Moon, because getting into Martian orbit, landing, and climbing back off Mars are inherently larger energy demands. Ceres, sitting deeper in the solar gravity framework, comes with its own distinct energy tax. That deeper position in the asteroid belt could demand far longer, slower, and more patient travel strategies. This is where propulsion types start changing everything. For Mars missions, chemical propulsion, the traditional rocket systems we use to hurl payloads at high speed, still dominate the conversation. But for Ceres, a different type of travel begins to emerge as the frontrunner: electric propulsion. It's less about high-speed bursts and more about efficiency over time. Technologies like ion propulsion can keep pushing a spacecraft gently over long periods, making them immensely efficient for cargo or robotic missions that don't have the same human urgency. That creates an ironic reality. Reaching Ceres could, in some scenarios, require less overall energy per kilogram of payload than Mars, but only if you have time to spare. Robots, tankers, and satellites don't care if they get there late. Humans certainly do. And here's where the debate takes a real turn. When it comes to deep space, you can't lump all mission types into one big bucket. If we're talking about robotic cargo missions where slow and energy efficient options work just fine, Ceres becomes much more competitive. A robotic ship doesn't mind years in transit as long as its systems are engineered to last, and it can fulfill its purpose when it arrives. If the question shifts to what's the better first major cargo hub, then suddenly Mars isn't the runaway winner. Ceres starts sounding reasonable, even practical. You could imagine robotic tankers ferrying water or fuel to serve orbiting stations or delivering critical materials for deeper space missions. Humans, though, introduce a much more delicate balance. If the conversation is about where we send a crew next, the calculus changes dramatically. You can't just ask people to survive multi-year journeys casually. Life support, radiation, and psychological burdens stack faster than any robotic system can compensate for. Imagine the repercussions of a mishap 3 years into a mission, still far from the destination or return help. A robotic mission delayed by years can still be worthwhile. A human mission delayed by months could be catastrophic. This is why comparing Mars and Ceres as destinations for humans and robots simultaneously is misleading. It's almost comparing apples to oranges. They serve radically different audiences with radically different needs. Mars has something else going for it that can't be ignored. Decades of preparation. Missions to Mars follow reliable windows of opportunity that open approximately every 26 months, thanks to the alignment of Earth and Mars in their orbits. This predictability means not only efficient mission planning, but also a rhythm of repetition. We've studied how to land robots on it. We've thought deeply about how to preserve habitats there. We've even drilled into spacecraft architectures for Earth return and surface exploration. Mars hasn't just been physically closer, it's been institutionally closer. The groundwork for reaching Mars is so advanced compared to Ceres that even Mars's enormous challenges are filtered through a much more mature and experienced lens. Ceres doesn't have that head start, and it's not just about technology, it's about institutional will. Most of humanity has never thought of Ceres as a destination, let alone a serious one, which means far fewer coalitions, mission studies, and funding sources exist to push for it. A crewed mission to Ceres might not have an engineering barrier that's fundamentally impossible, but it faces a staggering barrier in terms of readiness. Put simply, Ceres isn't just farther physically, it's farther in every sense of preparation. So where does that leave us? At the end of the day, it depends on what kind of transit goal we're trying to define. Mars wins in terms of speed. If the goal is to put humans on the surface within a time frame that feels achievable and tolerable, Mars keeps its lead. Ceres, on the other hand, might slowly grow into importance over time for a very specific niche. Minimum energy, automated cargo transport that prioritizes long-term efficiency over short-term arrival. As a human destination, Ceres is on thinner ice. As a logistics hub for machines, it's much more plausible. This is where the script sharpens its focus. Mars works for immediate human aspirations, but Ceres may one day emerge as the critical anchor for automated infrastructure. If that future materializes, then Ceres might matter, not because it's the end destination, but because it becomes the place that enables every place beyond it. Landing on Mars is an engineering gauntlet. You can't just think of it as a smaller Earth where you apply similar rules. It brings its own unique set of punishments for anyone trying to arrive in one piece. The thin atmosphere, for instance, is an almost cruel Goldilocks scenario. It's just thick enough to interfere with spacecraft descent, forcing you to account for heat drag and high-speed entry. But it's nowhere near thick enough to make landing easier in the way Earth's atmosphere does with parachutes and air brakes. On Earth, a parachute alone can do a lot of the work for you during descent. On Mars, nope. The air is far too thin for that simplicity. This leaves you in a tricky spot. Mars makes you burn in its atmosphere, shedding speed, but you still have a massive amount of energy to dissipate once you get closer to the surface. That's why almost every Mars landing involves multiple stages of controlled chaos. Atmospheric entry, parachutes that only work minimally, retro propulsion to slow you further, and finally a terrifying high-stakes decision moment as you attempt a soft landing. This combination of variables is why landing heavy cargo on Mars, like habitats, vehicles, or resource processing facilities, is so hard. You're trying to stop what's essentially a high-speed spacecraft with tools that barely work together. If this sounds like a nightmare to plan for, you're not wrong. Mars doesn't offer many second chances if something goes wrong during descent. Contrast that chaos with landing on Ceres, and suddenly the tone shifts. Ceres doesn't have an atmosphere to interfere with your arrival, but more importantly, it doesn't punish you with gravity on the way down either. The escape velocity at the surface, a measure of how fast something has to travel to leave the body without falling back, is only about 510 meters per second. That's around 1,700 feet per second if you prefer a number that feels closer to home. To make that intuitive, imagine a spacecraft speeding away from Martian gravity. That takes titanic amounts of energy and requires specialized descent vehicles. Leaving Ceres, by comparison, is much closer to climbing off a rolling hill than lifting off a planet. The tiny gravity well means it's not just easier to leave Ceres, it's also much easier to arrive. Without an atmosphere to slow you down, a lander can entirely focus on precise thruster adjustments, powered descent, and surface anchoring as its main challenges, rather than fighting against drag forces and chaotic heating. And because the surface gravity is less punishing, hardware doesn't need to be reinforced to the same extremes. Drop an expensive rover on Mars? You need to constantly worry about how its parts might break under those peculiar Martian forces. Operate a rover on Ceres? The stresses it will experience are entirely different and much gentler. But here's the kicker. As easy as Ceres makes landings and launches, that same low gravity complicates almost everything else. The stuff you take for granted on Earth, and could at least awkwardly manage on Mars, starts to feel profoundly unintuitive on Ceres. There's no weight holding machines, tools, or even people down. An excavator digging into the surface could push itself backward instead of scooping material forward unless it anchors itself properly. Throw in ultra-low gravity dust dynamics, where fine particles float and drift in unexpected patterns rather than settling naturally, and construction suddenly looks like a logistical headache. Imagine trying to build or maintain structures that constantly have to resist floating or shifting slightly due to almost laughable levels of gravity. On top of that, even something like walking becomes strange. A human pushing a heavy container across the surface is no longer just exerting force on the object, they are pushing against themselves as well, meaning a well-placed shove might send them floating rather than accomplishing the job. In short, low gravity is a double-edged sword. On one hand, everything is lighter, meaning energy costs for moving materials out of Ceres and into orbit are drastically lower. On the other hand, that same low gravity makes surface operations feel more like handling equipment in zero-G than like traditional terrestrial construction work. This doesn't mean it's impossible, it just means operating on the surface of Ceres would demand machines and protocols tailored more to engineering challenges in microgravity or shipyards than to handy tools designed for dusty Martian plains. And this is where the paradox really starts to take shape. If Mars is the place where humanity might truly begin living on another planet, Ceres asks us to think completely differently. Mars punishes anyone who tries to arrive or leave, but once you're there, everything about the planet demands that you stay. The gravity traps infrastructure effectively. Once you land heavy equipment, getting it back into orbit is such a massive undertaking that it almost never feels worth the energy cost. In some weird way, Mars forces you to think like a settler. You can't escape easily, so you adapt. That's why so many conversations about Mars involve sprawling surface operations, semi-permanent habitats, and visions of colonies. Ceres is the exact opposite. Once material is on the ground, leaving with it is cheap. It barely takes any energy to launch from the surface compared to Mars, or heaven forbid, compared to Earth. That means Ceres is practically begging to become an export hub, a place where mined materials, whether water, salts or volatiles, are gathered and processed only briefly before being shot out into orbit. The irony is rich. Ceres is incredibly easy to leave behind in a machine sense, but brutally harder to imagine as a permanent human home. Its low gravity makes it a dream candidate for industrial export and a logistics-based economy. Mars, meanwhile, is the harder place to arrive at and launch from, but it practically inspires humans to dig in and adapt. So which world is better at movement, really? If you're talking about moving people and their living ecosystems, Mars has a definite edge. It provides just enough gravity and familiarity to support an Earth-like rhythm for human society. But if we shift to moving goods, like exporting mined water, hydrogen, oxygen, or raw materials, Ceres suddenly starts winning. It becomes far easier to operate industrially rather than residentially. This leaves us in an odd conclusion that feels almost contradictory. Mars, the harder world to land on and leave, becomes the more natural place to stay long term. Ceres, the easier world to land on and leave, becomes a far better candidate for an operational hub but feels almost alien when discussing full-time human settlement. These contrasts define the trade-offs. The two destinations don't just exist in opposition to one another geographically. They ask humanity to make a fundamental choice about what we want to do out there. Is it people living their lives on a new planet? Or is it machines exporting materials into the framework of a new industry? Mars and Ceres embody those priorities deeply, and as we explore further, their strengths and weaknesses become even clearer. Gravity. It's one of those things that's so ordinary here on Earth, most of us don't even think about it unless we trip over something, or if we're watching astronauts float around playfully on the International Space Station. But when you start talking about building long-term outposts or even entire civilizations away from Earth, gravity transforms from an unseen constant into one of the most defining constraints of survival. And it's not just a matter of how much gravity you get, it's about how your body will respond to it over time, how it shapes your ability to work, and whether you can even call a place habitable in the long run. Mars, for all its challenges, at least gives you some gravity to work with. At 0.38 g, it's more than a third of Earth's gravitational pull, which might not sound like much, but is, in fact, substantial in practical and biological terms. Humans on Mars would still feel their weight, just reduced. An 82-kilogram person, about 180 pounds, would weigh closer to 31 kilograms, or roughly 68 pounds. You could walk, you could push, and things would feel lighter, but the sensations would still be recognizable. The body would still need to work against gravity to move, which is vital because our muscles, bones, and cardiovascular systems are trained through evolution to do exactly that. For a planet that is otherwise so hostile, Mars at least throws this important lifeline. Ceres, on the other hand, is in a different league entirely. Its gravity isn't just lower than Mars, it's almost negligible by comparison. At 0.028 g, which is the equivalent of less than 3% of Earth's pull, it barely even registers for human physiology. That same 82-kilogram person would weigh roughly 2.3 kilograms, or about 5 pounds. Carrying a heavy piece of equipment might feel like lifting a briefcase, and a small push off the ground could send you into a slow-motion float that arcs uncomfortably before you come back down. This isn't just a reduction in gravity, it's a shift into what's functionally an ultra-low gravity environment. The gap between 0.38 g and 0.028 g isn't a small fraction to argue over. It's a complete category jump. And here's why that matters. We already know how dangerous low gravity is for human biology. Decades of microgravity research aboard space stations have shown that the body deconditions quickly when gravity is removed. Muscles atrophy because they're no longer resisting gravitational pull. Bones lose mass because they're not carrying weight. Fluid shifts occur in the cardiovascular system. Blood doesn't circulate the same way, and many astronauts experience vision impairment from pressure changes in the head. What's more, exercise on Earth, an elective lifestyle choice, becomes mandatory in low gravity just to slow down the process of breaking down. Mars's 0.38 g might mitigate some of those effects by giving the body something to work against. Ceres, with 0.028 grams, probably doesn't help your biology any more than floating freely in space. If that's the case, then settling Ceres might not even be about working with the place's gravity at all. Instead, residents would almost certainly need to live in artificial gravity habitats, like those achieved through rotating systems, Spin a habitat fast enough and centrifugal force can simulate a certain level of gravity for the people living inside, but that changes the entire concept of settlement. You're not living on Ceres in the way that people imagine living on a planet or moon. Instead, you're operating out of entirely self-contained environments that simulate Earth-like conditions, only venturing down to the surface temporarily to mine resources or perform other tasks. Now, let's talk long-term, and not just long-term for individuals, but for entire societies. Adults can barely maintain their health in low gravity, even with countermeasures, but let's say we figure out how to get people to survive. Survival isn't the same as thriving as a species. If you're really serious about calling a place home, you're imagining children being conceived, born and raised there. You're imagining an ecosystem, not just for the microbes or crops, but for humans themselves. On Mars, at least, there's a plausible middle ground. With 0.38 g, there's a chance that pregnancy, development and growth might proceed closer to Earth norms, but at 0.028 g, the uncertainties compound exponentially. Embryos, developing bodies, and growing bones could face conditions so alien that normal development becomes unlikely. It's not just about having babies, it's about whether those babies can grow into adults who thrive in a new gravitational paradigm. And then there's the question of day-to-day work. You might think low gravity makes everything easier. It's true that you can lift heavier objects, for example, but physics can cut both ways. Carrying equipment might demand fewer resources, but stabilizing yourself when using tools becomes trickier. Push against something forcefully, and you're just as likely to push yourself out of position as you are to move the object in question. Accidents might look different. Falls are slower, but momentum becomes stranger to manage when you're almost weightless. Simple physical labor becomes less intuitive. By contrast, Mars' 0.38 g might strain your joints more and require heavier lifts, but it allows more natural movement overall for both humans and machines. The combination of these small stresses during operations, stabilizing equipment, anchoring systems, moving materials, might make Ceres a place where human labor starts to feel awkward and inefficient without extensive counter-engineering. So what does all this tell us about how gravity shapes these two worlds? It might just decide the whole argument. Mars, despite all its challenges, gives you a chance to create something that looks like a functioning human environment. Gravity is enough to foster semi-natural movement, to possibly allow biological systems to stabilize, and to at least give us a chance to push the limits of life in a new, harsh world. Ceres, though, virtually writes itself out of contention as a natural habitat. That's not to say humans can't go there. They can, but if they want to stay for long periods, they'll almost certainly be doing so in rotating stations designed to mimic Earth gravity. And that's not the same thing as building a city on a surface. If anything, it's closer to building a supply base for orbital factories, not settlements. This makes the fundamental difference clear. Mars might not just be kinder to human life, it might be the only realistic shot at a world humans can live and grow on naturally. Ceres, unless massive technological strides make ultra-low gravity irrelevant, will never truly be a home in the way people imagine planets can be. It won't sprout multi-generational civilizations. Instead, its role becomes purely practical, a logistics hub, maybe the industrial backbone of the asteroid belt, but always more about service than residence. In that sense, if we're not building artificial gravity stations, Ceres isn't really a world in the human sense. It's a node, a tool, a crucial part of the system, but not the end destination itself. Radiation in space is one of those dangers that doesn't make for thrilling Hollywood visuals like asteroid impacts or explosive decompression, but it's arguably the stealthiest and most constant killer humanity faces as we move off Earth. And the thing most people don't realise is that the radiation problem doesn't start when you reach the surface of your destination. It actually begins the moment you leave the shielding cocoon of Earth's magnetic field and atmosphere. Space is filled with invisible enemies, galactic cosmic rays that penetrate the body at a subatomic level and solar particle events, bursts of charged particles from the sun that can overwhelm any spacecraft with life-threatening energy. It's like being in a constant low-level drizzle of atomic bullets, punctuated by the occasional hurricane. The longer and farther you travel, the more exposure you get. This is where Ceres starts off at a disadvantage. The simplest reality of the situation is that the trip to Ceres is, by default, longer than the trip to Mars. For current propulsion technologies, a mission to Mars might involve 6 to 9 months in transit, one way. For Ceres, you're likely looking at 2 to 3 years using similar technology. That's 2 to 3 times as much cumulative radiation exposure just on the way there. And that's under the assumption that your ship has excellent shielding, and that it's not exposed to an unusually large solar event during the trip. Every extra month in space means extra risk of damage to the crew's DNA, increased cancer risks, potential neurological effects, and other long-term health consequences we're only beginning to understand fully. Without major improvements in propulsion technology, like faster nuclear-powered or advanced electric drive systems, Ceres simply comes with a higher radiation bill before you even step off the ship. Once you arrive, Mars offers astronauts a curious kind of help with this problem: its atmosphere. Now don't misunderstand, the Martian atmosphere is thin, 99% thinner than Earth's, to be precise. So it's not like you can walk around expecting it to protect you from cosmic rays the way Earth's atmosphere does. But even this whisper-thin layer of carbon dioxide provides some shielding value. It reduces the number of high-energy particles slamming into astronauts on the surface by about half. That definitely doesn't mean you can survive unprotected long-term. Living on Mars still requires a pressurized habitat with additional protection. But the atmosphere, combined with the planet's geology, provides options. Martian regolith, that dusty soil covering the surface, is dense enough to make excellent shielding material. If you bury habitats under just a few meters of it, you can cut down radiation exposure dramatically. Lava tubes naturally occur in caves formed by ancient volcanic activity offer another potential solution. They're ready-made spaces deep enough to shield future settlers from both radiation and micrometeorites. Ceres, lacking both an atmosphere and any substantial gravity, is a tougher nut to crack on this front. Without atmospheric protection, the surface is fully exposed to both galactic cosmic rays and the constant threat of solar particle storms. There's no natural place to hide. What you see is what you get. That being said, Ceres compensates for this disadvantage in one important way: its water, or rather its potentially vast supply of water-rich ice. Water is, hands down, one of the most effective radiation shielding materials we could hope for in space. Its hydrogen content makes it particularly good at stopping high-energy particles, meaning if you can access large amounts of water or hydrated minerals on Ceres, you can turn them into a huge advantage. Dig them up, extract the ice, and then use it to line the walls of habitats, shelter systems, and storage areas. This means a Ceres base could, in theory, build up its own robust radiation shields without needing to import extra mass from Earth, which is a massive cost saver. Mars also has water ice, of course, but here's the catch: it's buried deeper, harder to access, and requires more intensive effort to extract compared with Ceres' potentially surface-accessible supply. For radiation protection alone, Ceres starts to look less like a helpless sitting duck and more like a deep space bunker, if you're willing to put in the work to mine what you need. Radiation isn't the only invisible threat both destinations throw at humans. The cold is another brutal constant. Mars is ice cold by Earth standards, with average temperatures hovering around -60 degrees Celsius, or about -80 degrees Fahrenheit. But its proximity to the sun still provides enough light to generate a meaningful amount of energy for solar panels, provided you can keep clearing them of dust, which is always a problem on Mars. Still, solar power is viable with the right design, and nuclear or other backup power sources can step in to cover the gaps during dust storms or at night. By the time you reach Ceres, though, the sun feels noticeably more like a distant star than a warm source of light and energy. Ceres sits at an average distance of 2.77 astronomical units from the sun, nearly 3 times farther than Earth, meaning the amount of sunlight it receives is just over a tenth of what Earth gets. Solar power becomes much trickier in this environment. Even with advanced technology, the inefficiency would mean you'd need massive arrays to generate what a small system could handle on Mars. Combine that with the fact that the average surface temperature on Ceres likely hovers around minus 105 degrees Celsius, or about minus 157 degrees Fahrenheit, and you're dealing with a truly hostile thermal environment where power isn't just about running equipment, it's about staying alive. A sustainable base on Ceres would likely have no choice but to lean heavily on nuclear power or other non-solar sources, not just for electricity but to maintain livable temperatures within habitats. This introduces new challenges, as long-term nuclear infrastructure in deep space can be both expensive and controversial. So here's the quiet truth that emerges when you put all of these radiation and temperature factors together. Mars is the cleaner world in terms of energy and crew exposure timelines. With its atmosphere providing modest shielding, solar power as a viable option, and geologic features that enable effective habitat building, Mars offers pathways to settlement that are at least plausible with existing or near-future technologies. Ceres, on the other hand, feels more like a puzzle that isn't just technically complex but also economically and operationally steep. It can protect you from radiation if you exploit its water supply, but until you've built that infrastructure, the environment is far more exposed. And when it comes to power and heat, Ceres all but forces you to go nuclear, potentially cutting off certain financial avenues that would more eagerly fund Mars-like missions. And yet the answer still splits along familiar lines. If your priority is building habitable places where humans can live and thrive, Mars takes the lead. It simply accommodates our biology and infrastructure more naturally, or at least less unnaturally, than Ceres. But if you're thinking about heavy industry, deep space logistics, and resource extraction that supports other missions, then Ceres' combination of locally available shielding mass, weak gravity, and operational flexibility begins to make a much stronger pitch. It all comes back to what you value: survival and settlement, or production and expansion. Mars says live on me, while Ceres says use me. And which of those voices we choose to follow will likely dictate what kind of spacefaring civilization we become. If there's one single resource that can be called the true currency of space, it's water. And that might sound dramatic, but it's genuinely no exaggeration. In the vacuum of space, where every gram sent beyond Earth's gravity needs to be paid for with enormous energy and financial costs, water becomes something that's far more valuable than just a hydration source for astronauts. A kilogram of water, a single litre, can be split into its core components, hydrogen and oxygen, to create breathable air or rocket fuel. It can be used in life support systems to cultivate food, regulate temperature, or recycle waste efficiently. And perhaps most surprisingly, water is one of the best radiation shielding materials available, thanks to its hydrogen-rich molecular structure. Essentially, what might be an ordinary everyday liquid on Earth transforms into a multi-use, indispensable tool in the context of space exploration. But here's the rub. Bringing water from Earth into space is staggeringly expensive. Launching anything from Earth comes with a price determined by the planet's strong gravity. And water happens to be heavy. Each kilogram launched could cost tens of thousands of dollars, depending on the rocket and mission specifics. This means that any destination out in the solar system that offers abundant, locally accessible water isn't just a good idea, it becomes a logistical treasure chest. If you can extract and process that water on site instead of hauling it all the way from Earth, you're not merely saving money, you're creating a sustainable supply chain that could support exploration, industry, or settlements across multiple locations. This is where Ceres demands our attention. Ceres, the largest object in the asteroid belt, is widely believed to contain significant amounts of water ice mixed within its crust. Some models suggest that up to a quarter of its mass could be water in some form, whether stored as ice or chemically bonded to minerals. That's enormous when you consider the profound strategic value of water, not just as a utility but as a key to enabling entirely new forms of space infrastructure. If extraction becomes realistically practical, Ceres isn't just a dwarf planet anymore. It's a potential hub for what some visionaries call a depot economy, where missions travelling further into the solar system, toward the asteroid belt, the moons of Jupiter and Saturn, or even out to interstellar probes, could refuel, resupply, and continue their journeys without the burden of carting everything from Earth. Think of Ceres as a harbour, if you like, where passing ships refuel on their way to the wider cosmic ocean. The core idea here is rooted in simple physics. Launching water, fuel, or any other consumable from Earth is costly, not just in cash, but in energy, because Earth's gravity well is so deep. You need absurdly powerful rockets and massive propulsion systems to escape. Even Mars, which has its own water supply beneath its dusty surface and at its polar ice caps, doesn't compete well with Ceres in this regard. Why? Because Mars's gravity is still significant. While far weaker than Earth's, it's enough that launching materials, and this applies to water just as much as anything else, requires its own complicated, expensive ascent architecture. Essentially, anything you want to haul off Mars is going to need more energy, a larger launch vehicle, and bigger logistical costs than the equivalent from Ceres. Ceres, by comparison, barely has any gravity to fight. As we've already explored, it's so small, and its gravitational pull is so feeble, just 0.028 g, that getting something into orbit there takes a trivial fraction of the energy required on Mars. Water mined on Ceres could be efficiently processed into liquid hydrogen and oxygen and then launched from its surface with far smaller propulsion systems. That weak gravity makes it easier to move mass out of Ceres and distribute it elsewhere, whether to orbiting depots, passing spacecraft, or other bases in the asteroid belt. It becomes much less of a place to settle and far more of a station, a logistics node designed for extraction and redistribution. Now, it's important to clarify that Mars also offers water, and it does so in ways that support its own settlement logic. A colony on Mars could use its local ice deposits for agricultural feedstock, habitat support, and even localized fuel production, turning it into a relatively self-sufficient environment for its residents. That's crucial for a settlement-oriented strategy. But here's the key distinction. Mars's water is ideally suited for local use. It's not the kind of accessible, export-minded supply that Ceres' smaller gravity well enables. When you think about exporting water or any of the resources derived from it, like hydrogen, Joule, and oxygen gas for rockets, Mars starts to look like a weightlifter training in a swimming pool. The potential is there, but every move is slowed down by the reality of climbing away from its gravity. Ceres is much leaner, and in this economic narrative, that makes it far more agile. Here's where the broader implications become clearer. If you're looking at the solar system as one giant exploration map, Ceres isn't the place you'd choose as your primary destination for humans to flourish, but it might very well be the place you put on the map that says, this is where we'll refuel, reload, and prepare for the harder, more distant challenges ahead. It's a stepping stone with enormous leverage, what some might call a fuel depot, or staging ground for missions heading not just outward toward Jupiter, Saturn, or the icy worlds beyond, but also inward as missions return closer to Earth. This completely changes the geometry of exploration. Instead of designing every mission to carry everything it needs for years of travel at immense cost, you create a network. Ceres becomes part of that network, a harbour that ensures the flow of resources between planets and asteroid stations. And this is the shift in thinking that Ceres forces. It challenges the way humanity even conceptualizes its space exploration ambitions. Mars makes you dream of settlement, living on a new Earth-like surface, struggling against harsh conditions, adapting, until one day maybe it feels like home. Ceres doesn't inspire you to imagine planting your flag in its dusty crust or raising generations of human settlers there. What it does is push for something more functional, more strategic. It's not move all humans here, it's use this resource point to make everything else easier. That's a quieter argument, maybe even less romantic, but it's no less critical. If we're thinking long-term about a space economy, about building the transportation pipelines, the refueling stations, and the supply chains that will eventually let humanity operate freely in both the inner and outer solar systems, Ceres has a clear edge. Its water, its low gravity, and its position as the largest body in the asteroid belt make it uniquely suited to support those large-scale industrial needs. The question then shifts sharply. Are we building for ourselves as settlers clinging to a new home? Or are we building for the machines, the networks, and the infrastructure that humanity will rely on in the centuries to come? It's here, when you frame the issue entirely around logistics and resource movement, that Ceres starts to pull ahead in certain ways and even, in a narrow but important sense, starts winning. Mars makes sense as a settlement candidate. Ceres makes sense as an enabler, a key that unlocks the movement of resources and the sustainability of exploration. They're not trying to beat each other at the same game. Mars is the city, Ceres is the harbour, and if space truly is our next frontier, then you need both to make the future work. Building habitats on Mars feels like the kind of grand challenge humans were born to dream about. Picture it, a base set on the dusty red plains, maybe dug into the natural terrain or sheltered under domes that glint under the weak sunlight. You'd have greenhouses where crops grow in carefully controlled conditions, pressurized tunnels connecting labs, residential pods and workstations, and maybe even rovers crisscrossing between outposts exploring the surrounding region. Over time, you could imagine such a base expanding, becoming almost like a town. Lava tubes beneath the Martian surface, naturally protected from radiation and temperature extremes, could house entire networks of shelters and research installations. People might build infrastructure to extract resources directly from the regolith, or begin constructing pressurized industrial zones. Even if these ideas come with enormous technical difficulties, they feel familiar in concept. It's frontier building, plain and simple, a new chapter of humanity venturing into a harsh but tangible world and slowly making it livable. Ceres, on the other hand, doesn't lend itself to that kind of narrative. The conditions force an entirely different mindset. A Ceres base wouldn't feel like a town breaking into the wilderness. It would feel more like an engineering installation dropped into an alien world with one primary purpose: survival and utility. The first base on Ceres would almost certainly look less like a settlement and more like a mining station fused with a submarine lab. Imagine a small, heavily controlled outpost where every system is engineered with precision: life support, thermal regulation, radiation shielding. Any habitats would likely be buried beneath regolith or sealed inside artificial constructs to protect against the constant radiation exposure from space. This isn't the romance of neighbourhood building. It's the grit of surviving and operating in a place made for function, not for human comfort. The tone matters. On Mars, people dream of building colonies, growing food, and carving paths into a new world. On Ceres, it's more about the discipline of industrial survival and heavy mechanization. Every decision has to serve the mission: mining or maintaining fuel production, transporting resources. For this kind of base, using robotics to handle the lion's share of surface work might even make more sense than relying on human labour. The emotional experience of a Ceres base would feel less like pioneering and more like operating. The human element is secondary to the utility of the base itself. Now there's another layer that completely shifts how habitats would be designed on Ceres compared to Mars: gravity, or the lack of it. This single factor could make or break the way humans imagine living on Ceres for any substantial period. Humans evolved to live under Earth's 1g of gravity, and over decades of research on microgravity, we've painfully learned that the absence of strong gravity wreaks havoc on the human body. Remember, Ceres only gives you 0.028 g, so low it's practically irrelevant for maintaining human health long term. If that's the case, then living on Ceres isn't a matter of adjusting to the environment. It's a matter of outright defying it. The most practical solution would involve artificial gravity, created through rotation. That starts redefining what living on Ceres actually means. You might not sleep or work on the surface at all. Instead, humans might live inside rotating habitats, either in orbit above Ceres or tethered to anchored structures on the surface. These spinning systems would create centrifugal force to simulate gravity, offering some of the physiological benefits of living in a gravitational field. That's a huge architectural difference from Mars, where partial gravity, while far from perfect, may allow people to live directly on the surface without needing to entirely abandon normal biology. On Ceres, artificial gravity might move from a luxury to an outright necessity for human health. Think about what this means for the emotional sense of what it is to live on Ceres. You wouldn't have simple surface bases, interconnected by breathable environments, as you might dream about on Mars someday. Living on Ceres might become a little more like working on an offshore oil rig, where your habitation systems are entirely separate from your work site. People might only go down to the Ceres surface temporarily for mining shifts or resource operations before returning to the safety of the rotating habitats. You wouldn't be living on Ceres in any meaningful sense. You'd be living with it as part of a larger logistical system. It's a fundamentally different relationship to the environment. The tools would also reflect this difference. On Mars, surface construction makes sense in the context of partial gravity. Martian regolith can be common building material, processed into bricks or used to fill radiation shielding berms. Heavy machinery could work semi-normally, though adapted for the weaker gravity and dustier conditions. Ceres changes everything. The ultra-low gravity means tools and construction systems need to be built with entirely different assumptions. Anchors and tethers, rather than weight, would likely be critical for stabilizing both machinery and human-operated tools. Excavators, for example, might need not just to dig but hold themselves firmly to the surface while doing so, possibly with clawed stabilizers or anchored treads. Construction in such an environment wouldn't look like a frontier town slowly building itself outwards. Rather, it would be sealed, modular, and inherently temporary, designed to work symbiotically with the low gravity rather than trying to fight it. Even the available materials on Ceres tell a different story. Mars offers some elements of an ecosystem: regolith, metals, ice, and sunlight for those who want to take their chances with solar power. Ceres offers resources too, but they're tuned for entirely different needs. Excavated ice, hydrated minerals, and rocky feedstock dominate the conversation, but how those are used depends almost completely on whether they're staying on Ceres or being distributed through the greater space economy. In other words, everything about how and why you build on Ceres is transactional and practical. Nothing about it lends itself to the kind of organic, slowly evolving environment humans imagine in Martian colonies. It all boils down to the shapes we dream about when we think of each world. Mars invites images of domes, habitation modules on the plains, and connected neighborhoods under alien skies. These are grand, ambitious architectures, attempts at making the surface livable no matter how monumental the challenge. Ceres, though, pushes human imagination in a more industrial direction. Its habitats aren't places to build societies. There are pockets of survival and infrastructure designed to make the rest of the solar system open to exploration. This means the look of Ceres isn't a city spreading across a dwarf planet. It's a network of workstations, storage depots, and operational bases where humans interact selectively. And that's where the deeper realization lies. Mars, for all its difficulties, is an invitation to think about what it takes to translate earthbound concepts of life into new planetary frontiers. Ceres isn't asking for that. It's pushing humans to think like systems builders rather than settlers. One world invites us to grow into it, however painfully. The other invites us to use it, however purposefully. Neither vision is wrong, but they're telling us something very different about the kinds of futures we could create, and the kinds of tools we'll need to make those futures real. Food, air, and life support. It's the trifecta of existence, and it's something that no human mission can go without. But when you're talking about destinations like Mars or Ceres, these aren't just logistical checkboxes to tick off. They're the foundation of whether life in these places feels practical, possible, or just barely survivable. What's fascinating here is how different the solutions look for each world, and why Mars, for all its difficulties, seems like the more natural landscape for solving these challenges, while Ceres pushes us into the realm of extreme engineering and industrial problem solving. Let's start with food, perhaps the most symbolic piece of this puzzle. Farming is something deeply linked to human identity, digging into the ground, raising crops, feeding communities. On Earth, it's a practice that effortlessly ties humans to their environment. On Mars, though, farming is a fight. The planet offers no fertile soil, no soft rains, no breathable air to sustain plant life. And yet it still fits the mental image we associate with cultivation. Using Martian water ice, filtered and purified, settlers could potentially feed hydroponic systems or even small greenhouses. Advanced life support systems could recycle carbon dioxide exhaled by humans into a controlled atmosphere for crops. Artificial lighting, or if you're creative focused sunlight, could provide energy for photosynthesis. The challenges are massive, but they make sense in the grand scheme of earthborne farming pushed into an extreme alien environment. Mars has a few subtle advantages that help too. The day length, for instance, which is almost identical to Earth's at 24 hours and 37 minutes, provides a natural rhythm that crops might adapt to. Gravity at 0.38 g could also allow plants to grow in something resembling their upward, rooted formations, reaping enough directional cues to sustain healthy development. None of this erases the steep obstacles on Mars. Perchlorates in the regolith, chemical compounds that are toxic to plants, would have to be filtered out. Radiation levels demand habitats be either heavily shielded or subterranean. Pressure and temperature extremes mean every crop would grow inside tightly controlled spaces. And yet, farming on Mars feels narratively coherent, like another chapter in the long story of human resilience. You can imagine settlers eating their first Martian-grown potatoes and realizing they have taken a small but profound step toward calling Mars home. Ceres, however, throws all of that narrative out the window. Here, agriculture doesn't look anything like farming as you know it. In fact, calling it farming might be misleading. On Ceres, growing food would be closer to managing a biochemical survival system than nurturing plants in soil or hydroponics. The reasons are straightforward but unrelenting. First, sunlight is almost non-existent in practical terms. The dwarf planet's distance from the sun means solar energy is just a small fraction of what Mars receives. And even on Mars, the light is weak. Ceres would essentially force agriculture to rely on entirely artificial lighting systems, drawing their energy from nuclear reactors or equally intense power sources. That immediately shifts food production away from natural processes and into a setup where every watt of power has to be carefully rationed. And then there's the gravity, or lack thereof. At 0.028 g, roots might not know where to grow. Fluids inside them could behave unpredictably, failing to carry nutrients in a way that supports healthy development. In this kind of environment, the practical solution might not involve plants at all. Instead, bioreactors come into play, systems designed to grow algae, bacteria, or other microorganisms that can produce calories, proteins, and even vitamins in a far more efficient engineered process. That's the kind of farming that makes sense on Ceres, highly industrial, highly controlled, and far removed from the image of greenhouses and rows of crops growing under glass. It's not about watching food grow, it's about calibrating a system to make your survival calories on demand, no matter how unromantic that might feel. Beyond food, the next part of the triangle is air, which is where things get even harder to compare. Both Mars and Ceres would require airtight habitats to support life, but here the broader environment shapes the sense of risk very differently. On Mars, you have enough volume, enough planetary scale, to imagine a range of systems working in tandem. Oxygen generators pulling CO2 from the small Martian atmosphere, plants contributing to atmospheric regulation, and recycling technology keeping the air breathable, even if a subsystem fails briefly. There's also the psychological scaling of Mars. Despite the near-deadly presence of the planet's surface, it still feels planetary. It feels like a place where dozens of separate systems could operate and overlap. Ceres, on the flip side, feels more like station life. Air wouldn't simply be one system among many, it would be one of a limited handful holding the environment together. Local water would likely be the key input for oxygen generation, with molecular splitting technologies separating it into breathable oxygen and hydrogen byproducts. But the margin for error would stay razor thin. Any failure in air processing, microbial control, or water recycling on Ceres wouldn't just jeopardize the base. It could rapidly expose the fundamental fragility of the entire operation. For a Ceres base to succeed, its residents would need to live with a level of constant vigilance over ecosystem management that Mars settlers might experience to a lesser degree, not because Mars makes it easy, but because it offers just a little more flexibility. That brings us back to the thing pulling all of this together: gravity, in this case biological uncertainty under low gravity. One of the least understood variables in deep space planning is how plants, microbes, animals, and humans interact in artificial ecosystems under partial or low gravity. At 0.38 g on Mars, you can at least imagine plants retaining the cues that let them grow up and roots digging down. Fluid dynamics behave strangely, but not so strangely that transportation systems shut down inside plants or animals. But Ceres? At 0.028 g, nothing operates the way it does on Earth. Not fluid flows, not weight dynamics. This difference changes how you build ecosystems entirely. Martian crops might struggle but remain recognizable. Ceres-based systems might push the concept beyond the realm of agriculture and into something closer to laboratory maintenance. You're feeding life support technologies, not ecosystems, and that leaves us with a massive question. Can a place where life only exists through extreme engineering ever stop feeling experimental? Can it ever feel like life is thriving instead of surviving? Mars might. It offers just enough similarity to Earth. Gravity, day-night cycles, the presence of natural rhythms, that you can imagine modular ecosystems evolving alongside human settlers. You can picture it not just as a place where food is made, but where a small but functioning cycle of life begins to take root. Ceres, though, you don't build ecosystems there. You build tools, systems, and backup systems that keep those tools working. Food doesn't grow, it's manufactured. Air doesn't filter through an ecosystem, it gets processed, recalibrated, and filtered by human intervention. And that's where this entire discussion about food, air, and life support draws sharp lines between Mars and Ceres. Mars keeps at least some of the romance alive, the struggle to turn a barren land into a living one. Ceres strips that away and asks for something colder, more precise. It's not about thriving naturally, it's about survival, industrial-scale processes, and constant management. That reality doesn't disqualify Ceres, but it does mean it fits into an entirely different role. Mars makes you think about settlements, about budding civilizations, and about how humanity once farmed on Earth and can do so again on other planets. Ceres makes you think about supply chains and production pipelines. Mars feels like it could nurture life. Ceres feels like it sustains operations. And in those two statements lies the entire essence of the comparison. Mars is a planet that for billions of years seemed poised to be Earth's sibling, a terrestrial world warmed by sunlight, shaped by rivers and lakes, and perhaps carrying the ingredients for life itself. And yet, something happened to Mars. At some point in its deep past, the planet began to lose its grip on its atmosphere. Its climate cooled, liquid water dried up, and the environment transformed into the barren, dusty landscape we see today. But here's the thing, that transition, that story of how Mars went from a potentially habitable world to a frozen desert, is a mystery that holds enormous scientific value. In every canyon, every ancient riverbed, every weathered mineral, Mars offers pieces of an unfinished puzzle that could teach us not only about the planet's history, but about Earth's, and even about the broader universe. Mars is extraordinary because it allows us to study a failed Earth up close. Its geology invites us to dig into the layers of its past and reconstruct its climate history. How much water once flowed here? Did it pool in oceans, deltas, and lakes for millions of years? Or did it come and go in short bursts? And the biggest question of all, did life ever emerge on Mars? If the answer is yes, even if it's buried in fossils of microorganisms trapped deep in Martian rock, then the implications are staggering. Life transformed Earth very early in its history. If it appeared here and on Mars independently, then it would suggest that life might not be the rare cosmic exception we've long assumed it to be. If it didn't emerge on Mars, we still learned something just as important. What conditions close to habitability look like without tipping over into life. Every patch of ground on Mars is an opportunity to compare its evolution with Earth's. Why did one remain lush and vibrant while the other became barren? How do factors like size, magnetic fields, atmospheric composition, and distance from the Sun influence a planet's fate? And what might this tell us about the fate of Earth itself, especially in the face of long-term climate challenges? Even as a cold, dead world, Mars has a life to it, a planetary-scale narrative that humans are eager to read. Now let's turn our attention to Ceres. It is not a failed Earth, not even close. Ceres does not pull at humanity's imagination in the same way Mars does, with its weathered canyons and reddish desert scapes that look eerily like high-altitude Earth. Ceres is smaller, colder, and sits deeper in the solar system. But what Ceres does offer, a scientific bounty of an entirely different kind, is no less profound. If Mars is a failed Earth, then Ceres is more like a time capsule from the solar system's infancy. It's not an Earth in the making. It's a memory, preserved almost perfectly, of how water-rich bodies formed and evolved in the asteroid belt. Ceres probably never had flowing lakes and rivers. Instead, much of its water is locked up in ice or chemically bound to salt-rich materials near the surface. Studying those water reserves could be like opening a door into the chemistry of the early solar system, helping scientists understand how water moved through space, how icy bodies formed, and how the building blocks of planets may have first come together. Those aren't trivial questions. Water's availability, or lack thereof, might be the single deciding factor for whether planets end up being habitable at all. By tracing the chemical and isotopic signatures in Ceres ice and minerals, scientists could get a better sense of which water-rich objects might have crashed into early Earth, delivering the oceans we rely on today. Ceres also holds clues to the distribution of volatiles in the inner solar system, compounds like ammonia and methane that play critical roles in shaping atmospheres and sustaining chemical evolution. Beyond water, the geological story on Ceres is unique. Its surface shows evidence of cryovolcanism, icy eruptions caused by subsurface water or brines slowly seeping to the top. It's not the kind of volcanic activity you'd find on Earth or Mars, where molten rock comes pouring out in dramatic flows, but it's volcanic nonetheless, frozen and otherworldly. These ice volcanoes, along with the salt deposits and deeply cratered landscape, make Ceres a standing mystery about what happens to a world when it doesn't quite reach planetary status. How does it live out its life geologically when it never gets large enough to heat itself internally like Earth, Venus, or even Mars? Here's where we pivot. Studying Mars and Ceres might sound like similar endeavours, but they're not. The tools and the questions differ dramatically. Mars benefits enormously from human presence. Picture scientists on the Martian surface, not robots but trained geologists walking through canyons, cracking open rocks in real time, improvising when a drill breaks, making judgment calls about which sample matters most. On Mars, sending humans is like upgrading from a magnifying glass to a microscope in terms of scientific capability. It's a large enough, diverse enough world that Fieldwork can transform our understanding of it. Ceres, on the other hand, doesn't call for wandering researchers exploring dramatic surface features. For one thing, its environment is inhospitable to that kind of exploration. For another, its scientific value likely lies more in precise, controlled sample collection. A human presence on Ceres might look less like geologists surveying the land and more like technicians operating mining and drilling rigs, refining our understanding of its composition through long-term infrastructure rather than short-term field studies. Robotics could handle a lot of what Ceres needs, but humans could make operations faster and more adaptive by maintaining and troubleshooting those systems when failures occur. It's less a world for exploration, and more of a world for extraction and processing paired with analysis. So now we're at the core question of this section. Which place teaches us more, and about what? Mars' undeniable advantage is its ability to hold a mirror up to Earth's history, and possibly its future. Questions about life, habitability, and planetary evolution are all civilization-level inquiries. Mars gives us startling insights into how fragile planetary systems can be, as well as inspiration to preserve and manage our own. Ceres, by contrast, doesn't hold that same mirror. What it does hold is a key to understanding the resources, chemistry, and processes that make space civilization practicable. While Mars tells us what to expect from terrestrial planets, Ceres tells us what's possible with the resource-rich bodies, how they preserve with us, how they locked in their volatiles, and how we might use that knowledge to transform space into a domain of thriving industry. There's no clear winner here, no easy choose one or the other decision. If you care about understanding the origins of life and the climatic fragility of Earth-like worlds, Mars is your bet. If you care about how a spacefaring future might operate logistically, finding resources, processing materials, building self-sufficient stations, Ceres unexpectedly rises to the forefront. What's fascinating is that even when applied to science, the same basic pattern we've seen throughout this script keeps re-emerging. Mars speaks to our instincts as explorers, settlers, and life-seekers. Ceres speaks to our instincts as builders, resource planners, and systems designers. Neither invalidates the other, but they ask fundamentally different questions about what it means to expand into the solar system. Let's step back and look at this through the lens of raw economics, because at the end of the day, nothing humanity builds in space survives on vision and romance alone. Money, resources, and logistics are what keep projects alive over decades and centuries. So which destination makes more sense in a future where space becomes not just a place of exploration but a functioning economy? The answer, unsurprisingly, depends on what kind of economy you're imagining. And once again, Mars and Ceres offer very different value proposition. Start with Mars, the poster child for humanity's off-world ambitions. While the dream of settling Mars carries enormous symbolic and cultural weight, turning that settlement into something financially sustainable is a very different question. A Mars colony would be staggeringly expensive to build and even more expensive to grow. Every habitat module, every tool, every kilogram of food in the early stages would need to be shipped from Earth into Mars' harsh environment, an economic bottleneck so steep that profit would likely be out of the question for centuries. Like any frontier, the costs of starting out in Mars are immense, and the return on investment is hazy at best. What could Mars offer then, as a way to justify these expenses over time? Tourism, possibly, though its reach would be limited to the extremely wealthy or symbolic gestures of goodwill towards science and exploration. Exports? That's even trickier. To make money exporting materials from Mars, you'd need to climb out of its significant gravity well, which means building large-scale ascent vehicles, possibly using locally produced fuel, a technology that might exist in time, but brings with it the fundamental question of, what are you exporting? High-value materials like rare metals or exotic compounds might make the case, but even then, Earth has no shortage of its own resources to meet demand. Manufacturing, maybe. A colony on Mars could eventually become a hub for specialized zero-G or low-gravity manufacturing processes designed for industries that work better in thinner atmospheres or weaker planets. But again, this would take centuries of build-up on Mars before the infrastructure would exist to run a functional, scalable, local industrial base. Right now, there's no clear financial model for Mars. What it does offer is something intangible but deeply compelling, the chance to be humanity's first planetary colony, an experiment in survival and the long-term resilience of human civilization. In simple terms, Mars makes sense as a civilization project first. What it doesn't make sense as, at least not early on, is a business. Ceres, however, tells a different story. Unlike Mars, where the primary value lies in building towns, exploring landscapes, and creating a foothold for humanity, Ceres is all about logistics. If humanity establishes an industrial network beyond Earth, the economics of Ceres start making clear, straightforward sense. Water extraction is the standout advantage. It would make Ceres one of the solar system's most strategically valuable bodies. Every kilogram of water mined on Ceres could be turned into rocket fuel, breathable oxygen, and radiation shielding. with the low gravity making it exponentially cheaper to ship out of its well than from Mars, or certainly from Earth. Propellant depots based around Ceres could serve as refueling hubs for spacecraft headed deeper into the solar system or for asteroid mining fleets operating in the nearby belt. In simple supply chain terms, Ceres looks like an economic powerhouse if we frame our economy around deep space travel. It's not the flashy destination students doodle onto their notebook as home of the first Martian dome, but it's the backbone that allows all those other ambitions to operate. Here's another factor: low escape velocity. Every kilogram of fuel, material, or manufactured good leaving Mars requires a significant expenditure of energy to climb out of its gravity well and reach orbit. With Ceres, that cost drops sharply. The weak gravity means exports are easier, cheaper, and less resource intensive. That could make Ceres not only a fuel and water hub, but also a viable location for staging materials for construction projects far beyond its orbit, like large-scale space stations, outer planet bases, or long-range interstellar missions. Economically, the difference between Mars and Ceres isn't just about proximity or resources, it's about energy costs and outputs. Mars holds resources for local consumption. Ceres can package and export them more easily across the solar system. But, and this is a massive but, Ceres doesn't make sense until there's a robust, functioning off-world economy in place. On its own, Ceres' water and resources are phenomenal, but have limited value unless there are customers to buy them. That means any Ceres-based economy depends on the existence of stations, spacecraft, asteroid mining operations, or deep space missions that need what Ceres can offer. In other words, Ceres isn't the starting point. It's an enabling step after humanity has already developed enough off-world presence to justify its role. Mars, by contrast, doesn't need these preconditions. It can be justified as a standalone project symbolically much sooner because of its broader cultural meaning as a backup world or proof of concept for planetary colonization. Mars has value simply as Mars. Ceres is only economically compelling when paired with everything else humanity builds between planets. This is where the difference between export value and local value becomes essential. Mars excels at creating local value, a settlement with habitats, research labs, localized agriculture, scientific exploration, and eventually a growing population. It doesn't depend on shipping products off-planet to justify its existence. Instead, every resident, every scientific breakthrough, and every tractor planting Martian crops reinforces its importance. Ceres, by contrast, is all about export. Its value is tied almost entirely to moving things outward: water, fuel, volatiles, material. Ceres doesn't make sense as a place for humans to put down roots unless it's in service of creating the infrastructure that powers the rest of space. So here's the analogy. Saying which is better, Mars or Ceres, is like asking whether a farm is better than a harbour. Farms produce life-sustaining resources for their local communities. Harbours serve as critical hubs for trade and supply lines that connect distant locations across the globe, or in this case across the solar system. They're not trying to solve the same problem, but they're both essential to the system as a whole. Now for the verdict. If humanity remains mostly earthbound with just a few outposts or research stations here and there, mostly symbolic or scientific in nature, then Mars wins, hands down. It fits the story humanity is already telling itself about space exploration, building a permanent home on another planet and expanding civilization to ensure species survival. But if humanity enters a long-term phase of building industrial networks in space, mining asteroids, constructing massive orbital structures, sending missions to the outer planets, then Ceres will swiftly rise in importance. It won't look like the romantic dream of interplanetary civilization. It will look like the practical logistics economy that makes that dream achievable. That's the true distinction. Mars is the more likely first destination, but Ceres might become the reason we're able to go from one planet to many. It's not the first choice, it's the pivot point that could unlock the rest of the system. When talking about setting up life far from Earth, the obvious focus is always on the technical barriers: air, food, radiation, water. But humans don't just survive off systems and resources. At some point, As harsh as the environment may be, they need to feel something more, something that connects them to the place they're living in. This isn't just fluff. It's a core part of whether people not only stay in a destination but build lives there. Psychology, community, identity, and even just a sense of home are massive influences in whether a settlement is sustainable in the long run. And when it comes to that intangible but crucial side of belonging, Mars has a compelling, if subtle, edge over Ceres. Let's start with Mars. Even stripped down to raw facts, Mars feels like a world. It has a horizon you can see as you stand on its surface, a sky, thin and reddish pink though it may be, that arcs overhead. It has terrain you can walk across. There are hills and craters and plains, natural features you might navigate if you were exploring with rovers or on foot. Mars has seasons driven by its tilted axis, giving the planet a rhythm that human calendars could adapt to. Its days are close to Earth's, just 24 hours and 37 minutes long, which gives people a daily pattern that's eerily familiar. There are even weather systems, including dust storms and whiffs of atmospheric activity, that make the planet feel alive in its own alien way. All of these things, on their own, might seem small compared to the planet's radiation, thin atmosphere, or freezing temperatures, but together, they make Mars feel less like a space station attached to a barren rock and more like a location, an actual place. That psychological framing matters because human beings are hardwired to need somewhere to call home. Mars's hardships don't erase those psychological anchors. If anything, they enhance them. Life on Mars will be relentless. Radiation exposure, sealed habitats, constant problem solving to keep systems functional. And yet, you could still look out the window and see a world stretching out into the distance. You could mark the rise and fall of the sun without it feeling like an abstraction of time created by machinery. To live on Mars is to live on a planet that humans can start thinking of as theirs. Even in its starkest moments, Mars provides theirs, a feeling that you're somewhere rather than nowhere. Ceres, by all accounts, won't deliver that same psychological experience. Let's say you're living on Ceres in a future settlement. What's outside? There's no real horizon. Its tiny size and low gravity make it feel less like standing on a planet and more like standing on a large asteroid. Its surface, bathed in the dim light of a sun that seems as distant as a star, doesn't shift or cycle in ways that easily map to human intuition. With no real atmosphere, no weather, and no terrain features expansive enough to explore like a landscape, everything about Ceres feels enclosed. Habitats on Ceres, already buried for radiation protection, would likely cut off residents from most direct interaction with the environment. In some ways, life on Ceres would be closer to living inside a polar submarine base, tethered to critical systems and maintaining a constant vigilance over operations. Now, that's not necessarily bad. There are people perfectly suited to living in those kinds of settings, airtight, mission-driven, specialist lifestyles. What a Ceres settlement would most likely not do, however, is develop into the kind of sprawling, socially rich environment we associate with human towns or colonies. It's hard to build families, communities, or even long-term social stability when the physical environment treats you more like a visitor than a resident. Until artificial habitats start spinning massive levels of artificial gravity in orbit, or building centralized communities and clusters, a settlement on Ceres would probably feel more like a remote industrial facility than an early-stage civilization. That may work just fine for rotating crews of workers, operators, and engineers handling mining or logistics. What it doesn't scream is home. Identity plays a huge role here. Imagine living on Mars for a moment. Over time, as settlements grow, so does the potential to develop a uniquely Martian identity. The environment feels planetary, it's large, it's territorial, and it holds the human imagination. On Mars, those living there could define themselves as Martians, not just by location, but because the world itself shapes part of their story. Living on Ceres, however, that's a harder identity to anchor. The environment doesn't feel planetary in the same expansive sense. Instead, Ceres might feel like a node, a workplace, a connection to a grander system. You would get titles like belt workers, miners, or station crews. These labels reflect purpose, function, and networked logistics, but they don't suggest the kind of emotional connection to place that builds human identity and culture over multiple generations. One is rooted in territory, the other is purely operational. Then there's the elephant in the room: isolation. Getting to Mars is already a huge strain on human psychology. At best, missions could take about 6 months of travel with major implications for stress, interpersonal dynamics, and communication delays back to Earth. The first Martian settlers will have to live with the knowledge that Earth sits tens of millions of kilometers away, with signals taking tens of minutes to travel round trip. But now take that psychological pressure and stretch it out even further. Ceres, being in the asteroid belt, could require 2 or 3 years of transit in the best case scenario, years of confinement before even getting there. Imagine how much strain that would add to the mental health of both the crew in transit and the inhabitants already stationed there. And once at Ceres, those communication delays stretch even longer, making correspondence with Earth not just slow, but emotionally fraught. Humans are adaptable, but stretch that isolation just far enough, and it pushes people into zones of stress that make building sustainable societies even harder. At the end of the day, humans are still humans. We don't just need air, water, and calories. We need a connection to land, or something approximating land. We need skies and patterns and features that convince us we aren't floating in the infinite void of space, that the ground beneath our feet is, in some deep way, our own. Mars, for all its dangers, offers those intangibles. Ceres doesn't. That's not a sentimental observation, it's a deeply practical one. People are far more likely to choose a world, even a harsh one, that satisfies their instincts about place, rhythm, and belonging. And honestly, that might just be the strongest practical argument Mars has in its favour. When the dust settles, as brilliant and useful as Ceres may be in an industrial sense, most ordinary humans will lean toward Mars because it offers what Ceres lacks: a sense of community, a sense of time, and a sense of somewhere. It's hard to put a price tag on something like that, but it might be one of the most important factors for humans moving beyond Earth. Mars has the aura of a world. Sometimes that's all it takes to build a future. When humans venture far from Earth, whether they're setting up scientific outposts, industrial hubs, or entire colonies, one thing inevitably becomes clear: distance matters, not just in kilometers, but in everything that distance represents. Communication delays, rescue complications, autonomy, governance, these things all change dramatically the farther out we go, and they force a rethinking of how we even structure society, authority, and resilience. In this context, Mars and Ceres offer fundamentally different challenges, and where one destination stretches the limits of independence, the other practically demands it from day one. Let's start with communication, because it's often overlooked in discussions about far-off destinations. On Mars, delays in communication with Earth are already a baked-in reality. Depending on the planet's alignment, radio signals between Earth and Mars can take anywhere between about 5 and 20 minutes one way. That means settlers or astronauts on Mars cannot call back to Earth for instant answers if something goes wrong. Every question, every instruction, every bit of guidance comes with a built-in lag, and that delay forces a certain level of decision-making autonomy on the ground. This is why so much Mars mission planning revolves around creating procedures, protocols, and training crews to solve problems without waiting for mission control to weigh in. The further people are from Earth, the more they have to act on their own judgment. Now, stretch that reality beyond Mars to Ceres. The sheer distance between Ceres and Earth takes communication delays to a whole other level. On average, Ceres is nearly 3 times farther from the Sun than Earth is, and at its closest it's still over twice as far from the Sun as Mars. That translates into signal delays that could reach well over an hour each way at certain alignments. Think about what that means operationally. A crew working at Ceres cannot depend on any form of near real-time guidance. A crisis occurs. You can ask Earth for help, but by the time they receive the message, analyze the situation and send a reply, precious hours could have passed. Every decision, every response to an emergency would rest almost entirely on the people who are there. Ceres changes the framework. A Mars crew operates autonomously out of necessity, but a Ceres crew must operate with a deeper level of independence baked into every action. Autonomy isn't just a convenience out there, it becomes the foundation of survival. And then there's the not-so-small matter of rescue. Any off-world destination has to assume that eventual rescue is at best a last resort. Space colonies, whether on Mars, Ceres or anywhere else, need to be as self-reliant as possible because Earth isn't sending help on short notice. But the degree of difficulty scales with how far you are. Mars, for all its challenges, offers backup potential within a somewhat feasible time frame. If something catastrophic happened on Mars and replacement supplies, medical equipment, or personnel were needed, a well-prepared rescue mission might be able to launch within a reasonable timescale, maybe a few months to get off the ground and another 6 to get there. That's long and precarious, but it's not insurmountable. A Ceres colony, on the other hand, wouldn't have that luxury. The outer distance of Ceres means rescue missions could take years to plan, launch, and reach their destination. If anything goes badly wrong, whether it's a habitat failure, an injury requiring specialized treatment, or degrading equipment that can't be repaired locally, the crew may be on its own for far longer than any human mission has ever endured. For Ceres to be remotely viable, every piece of technology, every safety system, and every procedural safeguard would need to operate to an almost flawless degree. Redundancy wouldn't just be nice, it would be life or death. Now, let's step beyond the technical and operational challenges and look at something even broader. Governance. As communication delays grow and physical isolation deepens, how do you govern a settlement's behaviour when they are functionally beyond the reach of Earth? On Mars, it's not difficult to imagine a gradual evolution from a strictly overseen research base to a more semi-autonomous colony. Earth would still play a central role in shaping policies, but with round-trip delays of maybe 40 minutes at most, Martian settlers could reasonably expect to receive guidance while retaining considerable day-to-day self-governance. Over time, it's not far-fetched to imagine emerging Martian institutions managing civic life, lawmaking, or even taxation independently. On Ceres, however, things might look different. The nature of the place, a logistical hub, an industrial outpost, a mining facility, brings with it a different set of governing pressures. Unlike Mars, which invites civic-minded progression, Ceres would likely start life as a heavily industrial site. Corporate interests could dominate early governance, especially since Ceres' role revolves around exporting extracted resources rather than creating settlements designed to thrive independently from Earth. The questions start itching uncomfortably here. Would Ceres become a company town writ large? If companies control the key infrastructure, fuel depots, water extraction systems, export logistics, how much freedom would workers or operators really have? Does the economic focus on resources make governance there less democratic and more hierarchical? These are not far-off concerns. Industrial environments, especially ones this isolated, often concentrate power in the hands of whoever controls the supply lines. That industrial control also introduces a layer of strategic tension. If Ceres becomes the solar system's refueling station or a key hub for water and resource distribution, it gains enormous importance, not just economically, but strategically. Whoever holds Ceres doesn't just run a dwarf planet. They potentially control the flow of materials that other space missions need to survive and operate. Access to propellant depots or water reserves becomes a point of leverage, one that could influence exploration budgets, mission plans, and potentially military strategies. Mars, in contrast, holds symbolic and demographic value. Controlling Mars might make you important, but controlling Ceres might actually give leverage over supply chains. Think of it this way. Mars is about people. Ceres might one day be about power, a power rooted in logistics, not population. Which one is more impactful depends on how humanity's priorities evolve. Lastly, there's a moral and social question that needs asking. Which destination is easiest to govern humanely? Mars, with its high potential for civic growth and population diversification, could evolve into something approximating a full-blown planetary society, Democracy, or at least participatory governance, fits more clearly into that environment. Ceres, by contrast, feels more transactional. Its early existence would rely so heavily on industrial needs and export-focused production that social diversity, family life, or even basic civic autonomy might not flourish for generations. If Mars offers lessons in how to build settlements like small Earths, Ceres may struggle with the lessons of workplace governance at extreme scale. Neither path is simple, but the trajectories point in very different directions. All of this ties back to the larger tension driving the Mars versus Ceres debate. The farther humanity moves from Earth, the more distance reshapes the systems that hold us together. Mars, while harsh, gives humans enough of a link to Earth, through communication, governance, and rescue potential, that it feels approachable. Ceres, by contrast, steps almost entirely into the realm of deep independence. You're asking not just about whether humans can work there, but whether they can live, adapt, govern, and cooperate when Earth becomes an afterthought. It's not just about finding the right rockets, habitats, or supply chains. It's about designing new models of civilization entirely. If we look at the near future, that critical first era of humans leaving Earth and establishing a permanent footprint in space, it's hard to ignore the gravitational pull of Mars as humanity's most likely next step. Pun intended. And while that pull comes from many directions, scientific, technical, psychological, it also comes from something a little less tangible but just as critical. The story we're already telling ourselves about Mars. It's not just an engineering challenge or a scientific dream. Mars has managed to embed itself firmly into the public imagination. That matters, because big projects like interplanetary colonization aren't just driven by technical blueprints. They are powered by narratives, by the ability to inspire people and get governments, private industries, and ordinary humans to funnel resources into a long, grinding process of exploration and settlement. Mars is, without a doubt, the planet that has captured humanity's attention. Part of that is its proximity. It's close enough to feel somewhat achievable. But part of it is the decades of groundwork already laid. Advocacy, mission concepts, technical development for entry and landing systems. These are not abstract ideas anymore. Organizations like NASA, ESA, and SpaceX have devoted immense amounts of energy into treating Mars as the next logical step after the Moon. Concepts for habitats, agriculture, localized fuel production, and rovers have been designed and debated over and over. Even in the public sphere, Mars has reached almost superhero status. Countless articles, documentaries, TV shows, and movies have turned it into a cultural symbol of humanity's ability to thrive under pressure. Compared to that, Ceres is just, well, it's in the asteroid belt. And though its water-rich nature and logistical appeal make it a smart industrial target, it doesn't yet live in the public's imagination, which means it struggles in the world of funding, storytelling, and the global push for certain kinds of missions. This isn't a minor oversight. In space exploration, perception can be as critical as propulsion systems when you're deciding what projects to prioritize. But there's also hard logic behind Mars' winning position. If we step away from the dreamy science fiction lens for a moment and look purely at survival-based instincts, Mars fits the backup world narrative much better than Ceres does. Species resilience, the idea of having a second place for humanity to thrive in case Earth faces a catastrophe, tends to drive a lot of arguments for expansion, whether we're talking about natural disasters, climate crises, or even existential threats like asteroid impacts. Mars simply has more of the baseline conditions necessary to support a self-sustaining civilization. It has land, real, open, walkable surface areas that humans can modify. It has local resources, ranging from water ice to minerals in the regolith. It has a day and night cycle that doesn't drift wildly from Earth's natural rhythm, and it has usable gravity in the form of its 0.38 g, which, while not ideal, is leagues closer to Earth-like living than the near microgravity on Ceres. These small but important intrinsic advantages make it far easier to imagine Mars hosting its own independent population, growing food, managing resources, building culture, than Ceres ever could without massive external support. Not everyone likes this backup world narrative. It has its critics, but it keeps showing up because at its core, it taps into something almost primal. People like the idea of a second Earth. Mars gets closer to that dream than any other realistic destination in our solar system. There's another reason Mars still outperforms Ceres in the near term: the idea of a proving ground. Whether or not Mars succeeds long-term as a major planetary settlement, it serves as humanity's best practice run for learning how to build sustainable societies off Earth. Think about what's required to make Mars work. Establishing agriculture in alien soil, mastering infrastructure for resource utilization like extracting oxygen from CO2 or water from ice, figuring out how radiation shielding works at a large scale, and managing a remote society that's light years away from the comforts of Earth's immediate technological support systems. These aren't just technical exercises, they're biological, social, and organizational experiments. Mars forces humanity to put together a playbook for how to live beyond Earth. Even if no Martian colony ever grows to the size of a city, the skills gained from trying agriculture, habitat design, and resource extraction build the foundation for humanity's next steps elsewhere. It's a school for becoming a multi-planetary species. You could argue that its success at being that proving ground matters far more than its success as a long-term colony. Ceres doesn't play that role nearly as well because it requires a different skill set. Ceres pushes lessons about logistics, mining infrastructure, low-gravity engineering, and robotics. Those are critically important for building a space economy, but less important as a first leap off Earth. If Mars teaches us how to live, Ceres teaches us how to operate. The distinction matters. Now here's where things get more nuanced. The timeline. Ceres, despite its appeal as an industrial hub and logistical powerhouse, doesn't fit easily into step one of humanity's expansion. Many of the advantages Ceres offers, a refueling depot, a deep space supply station, a hub for distributing water and volatiles, don't become relevant until the rest of the solar system is more developed. For example, without established asteroid mining operations or missions headed to deeper regions like Jupiter or Saturn, Ceres resources don't have enough demand to justify large-scale investment. Its advantages blossom in a scenario where there are already multiple players in space, orbital stations, asteroid miners, scientific missions, even small colonies that need what it can provide. That makes it a second-stage candidate. Mars, by contrast, fits right into step one. You don't need space economies or advanced infrastructure elsewhere to justify a push to Mars. It stands on its own as a milestone destination. And yet, asking about Ceres now, raising the question of whether Ceres has merit, is not just fair, it's smart. It stops the global Mars-centric conversation from becoming too complacent. Mars is not going to fix every problem that space exploration poses. It's not a replacement for Earth, and it's not a shortcut to making the solar system work for humanity. When you zoom out and think about the purposes of expansion, what humanity truly wants to achieve off-world, Mars may answer huge questions about living, resilience, and survival, but it doesn't answer all the logistical questions about hosting networks of infrastructure and mobility. Ceres occupies that other category. Mars is about living on a planet. Ceres redirects attention toward what it takes to live between them. This kind of debate, Mars versus Ceres, isn't actually a competition. It's more of a lens to refine what success in space might look like. Mars feels like an endpoint, a goal in and of itself. Can we live there? Ceres feels like a key hidden further up the road. What makes the rest of the solar system accessible? 2 phases, 2 stems, but for now, in the immediate years ahead, Mars wins out. It's closer, clearer, and has much stronger momentum driving it forward compared to Ceres, which is still waiting for its moment to come. So after everything we've explored, habitat design, resources, mission timelines, sustainability, science, logistics, what's the final answer? Should humanity target Ceres instead of Mars for its next big leap into the cosmos? The answer reveals not just what is practical in this moment of history, but what kind of future we truly want to build. Mars and Ceres, for all their differences, serve two entirely different visions of humanity's expansion. One as a second world, a place to live and grow, and the other as the keystone that unlocks the broader solar system. So which one comes first? Let's break it down. If the ultimate goal is to build a human world, the answer is clear, and it's Mars. Mars offers something that Ceres simply can't. The possibility of fostering long-term settlements where humans don't just survive but start to build lives that feel, on some level, natural. Its partial gravity is low, yes, but significant enough to give the body a sense of orientation. Its day-night cycle is close enough to Earth's that biological rhythms can remain relatively stable. There's a surface, actual land you can explore and reshape. Resources are there, challenging but accessible, in the form of water, ice and minerals, and the sheer size of Mars provides the environment with a psychological weight that's impossible to match on a dwarf planet. Living on Mars, harsh as it may be, fits with the deep human instinct to settle and adapt. It's a stretch goal, a leap forward, but it matches our mental model of what it means to truly go off-world. Ceres, on the other hand, doesn't check those same boxes for settlement. Its gravity is too weak to promise any kind of biological stability. It has no natural land to cultivate, no spacious atmosphere to use as a shield or medium, and no horizon that gives it the emotional impression of a world. Building a habitat on Ceres wouldn't feel like living on a planet, even in the experimental sense. It would feel like living inside an industrial base. That doesn't make Ceres irrelevant, but it makes it a hard sell as humanity's next home. Mars challenges us to build a second Earth-like society under brutal conditions, yes, but the challenge at least aligns with an intuitively understandable goal: creating a livable world. Now let's flip the question. If the ultimate goal is not to settle but to build an infrastructure hub, then Ceres rises dramatically on the list of priorities. You don't go to Ceres to create a world for humans to stay permanently. You go to Ceres to extract resources, convert them into something valuable like rocket fuel, and distribute them throughout the solar system. Its water wealth, which could potentially be refined into oxygen and hydrogen propellants, shifts the economic story entirely. The low gravity, which makes launching materials cheap and efficient, further cements its role as a logistics hub instead of a city-building project. In that sense, Ceres doesn't have to compete with Mars on livability. It only needs to outperform Mars when it comes to usefulness at a system-wide scale, and it probably can, at least for specific goals like transportation, mining and refueling. As a resource hub that supports asteroid operations or acts as a staging point for missions toward Jupiter or Saturn, Ceres becomes incredibly valuable. It wouldn't host vast populations or sprawling civilizations, but it wouldn't need to. Its power lies in enabling everything else. This brings us to the smartest answer, really. It's not Mars or Ceres, it's Mars first, Ceres next. Mars is the logical first step because it teaches humanity how to live off Earth. It's the school where we learn the lessons of life support, agriculture, radiation shielding, social systems, and planetary logistics. It's the place where humans figure out how to build settlements that work in the long term. But once those lessons are learned and once we've started to make the solar system not just a place for exploration, but a place for ongoing industry, then Ceres becomes a key second step. It's easier to imagine Ceres taking on its role later in the timeline, as the pivot point that transforms the inner solar system from a destination mindset into a functional economy. What's fascinating here is how the choice reveals competing visions of the future. A Mars-first strategy says humanity still sees itself as explorers, settlers, dreamers building new cities and societies in harsh places. It's a vision rooted in resilience, optimism, and an almost romantic sense of expanding life to new worlds. A Ceres-first strategy says something different. It says humanity sees itself as engineers, manufacturers, and logistical thinkers who thrive in solving practical problems. It's colder, more calculated, more industrial. Neither of those visions is inherently wrong, but they lead to entirely different definitions of success. Mars feels like the future of settlement. Ceres feels like the future of infrastructure. Both matter, but which comes first tells us what kind of ambition humanity prioritizes in this century. And that brings us to the final line, the one that ties everything together. Should we go to Ceres instead of Mars? If we are looking for the next place to settle, to live, and to sustain a growing human presence, then the answer is probably not. Mars dominates the conversation when it comes to creating a second home for humanity. But if the question is about where to build the systems that unlock the rest of the solar system, then Ceres starts making a lot more sense. Mars looks more like a destination, a place you go to stay. Ceres looks more like a key, one that provides the resources and logistical framework to make humanity's expansion to other worlds possible. It's not about picking one over the other. It's about realizing that they represent two phases of exploration, tied together in humanity's long and complex journey into the stars. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.